Good morning, everyone, and thank you for joining us today. My name is Michael Kuhl, and I'm pleased to welcome you on behalf of Element Materials Technology to our webinar, HIRF Testing for Aerospace and Defense, Standards Overview and Practical Methods to Compliance. In a world of aerospace and defense, precision and reliability are mission critical. As aircraft systems become more complex and with the widespread use of composite fuselages and advanced avionics, the risks posed by high-intensity radiated fields, or HIRF, have never been greater. These electromagnetic environments can disrupt or even disable sensitive systems, making robust testing not only essential for compliance, but also for safety, performance, and program success. Today, our goal is to take the complexity out of HIRF testing. Over the next 45 minutes, we'll dive into standards that guide compliance, such as MIL Standard 464, RTCA DO-160, and key OEM-specific requirements, and explore proven testing methods that help programs stay on schedule. You'll gain insights into when to use direct illumination versus reverberation chamber testing, how to avoid the most common causes of failures, and practical tips for qualifying composite-based and next-generation platforms. Element has been working alongside aerospace and defense innovators for more than 50 years. And this webinar brings that hands-on experience directly to you. Whether you're developing new subsystems, navigating a certification program, or looking for ways to streamline your testing strategy, you'll walk away with knowledge you can apply immediately. I'm delighted to introduce our speakers today. Mark Sherman, Director of Product Qualification at Element, who brings more than 22 years of experience in MIL Standard and aerospace product testing, as well as Scott Carlson, Principal EMI Engineer at Element, with over 30 years specializing in HIRF, DO-160, and reverberation chamber design and execution. Together, Mark and Scott will guide you through today's technical content and share real-world insights from these decades of testing experience. We encourage you to submit questions throughout the presentation, and of course, I'm going to be looking and interrupting with those questions throughout, so don't be afraid to speak up on chat. We also encourage you to really stick around for our Q&A panel at the end, and we'll dedicate that last 15 minutes to answer as many questions as possible. With that, let's go ahead and get started. Mark, I'll hand it off to you, and we can get this train going.
Thanks, Michael. Appreciate the introduction and really looking forward to today's webinar. But first, I'd like to just take a brief moment to talk about our Product Qualification Testing Division, also known as PQT, where we perform HIRF testing here at Element. Our PQT labs can test to all iterations of MIL Standard 810, including the latest revision, MIL Standard 810H. Our labs in the US have the technical strength to support even the most complex programs, and we routinely support major test programs and design projects. Our tests here in the US are all run in ITAR and CUI compliant facilities, and we combine technical excellence with our project management experience, on-time delivery, and high capacity to support military, commercial, aerospace, and defense projects from start to finish. Here in PQT, we regularly perform to many major aerospace and defense standards, including MIL Standard 810, RTCA DO-160, and MIL Standard 461, of course. This next image shows our physical locations of our PQT labs across North America. These labs have over 200 environmental chambers, including tests like altitude, explosive atmosphere, temp, humidity, thermovac, salt fog, and many more. We also have over 120 dynamic systems throughout the organization to support your vibration and shock requirements, as well as the largest network of EMI chambers in North America, where we test from component level to full-scale vehicle testing in our large specialty EMI chambers. And lastly, I just wanted to cover some of our main departments here in PQT, from EMI testing to fire testing, hydraulics, dynamics, environmental, climatics, as well as our lightning test facility in Pittsfield, Massachusetts, where we do indirect and direct effects lightning to DO-160. And that's actually a great segue into our webinar here today on HIRF testing. You may or may not know lightning strikes are actually a natural source of a HIRF environment. So for today's webinar, we will provide an overview of the requirements of high-intensity radiated fields testing, where these fields originate, some practical methods testing both conducted and radiated, and some common pitfalls that we've seen over the years conducting HIRF tests. So without further delay, at this point, I'd like to turn it over to Scott to learn some more about HIRF testing here at Element. Scott, over to you.
All right. Thank you, Mark. Thank you, Mike, for the introductions. And yes, we'll be talking about HIRF, the high-intensity radiated fields. This is a topic that's very near and dear to my heart. And generating these fields has been well, over the last 30-some years has been difficult at best, but sometimes it's very interesting results. So we'll just launch right into it. HIRF is electromagnetic environment that is caused by strong electromagnetic fields. This is usually due to high power radio transmissions from all kinds of different sources. These RF fields can be very disruptive to electronic systems, especially to aircraft and other sensitive environments. A lot of times we'll find that these fields are very sensitive for the aircraft because of the fly-by-wire systems. So HIRF is electromagnetic field usually caused by radar. It's usually our high-power radio transmitters. Can also be created by lightning. Nearby lightning strikes create a very large magnetic field. If you think about a lightning strike, we're going to see about 1,000,000 volts. 1,000,000 volts at 100,000 amps, that's going to generate a very large spike of energy. And what we see that can actually do some pretty bad effects on the aircraft. And the field levels can vary drastically from hundreds of volts per meter to several thousands of volts per meter. This is largely due to the use of the aircraft. So if you look at a standard airplane, it's typically going to be about 3,000 meters away from the transmitters, whereas a helicopter can be up to 1,500 meters away from a high field transmitter. So those field levels are going to change roughly about 6 dB. It really depends upon the aircraft and everything else. To put this into perspective, the volts per meter that you would see on your common household items, they're going to see about 3 volts per meter. In a industrial environment, you're going to see around 10 volts per meter. Yet we're doing tests that are going to go up to 7,200 volts per meter for helicopters and to 3,000 volts per meter for aircraft on the outside area of the aircraft. So you can see how that can be a very daunting task to generate the fields, but also the more daunting task to be able to pass them. So that brings us to our first polling question. This is really so I can kind of tailor what we're talking about. And here's the first polling question. What is the largest roadblocks you're seeing to obtaining HIRF compliance? Lots of times understanding the compliance methods can be very difficult to understand. Passing the required test levels, that's one of the points where we're now ran some tests, we have some failures, and then determining the required test levels. Those can cause us to have some issues. And I'm going to open up polling for a little bit. So as we're looking at this, one of the things I find is the understanding the compliance methods. Until you're actually running the test, you almost always can't understand the compliance methods. There's several different methods to get to the compliance. And passing the required test levels, when you're looking at the test levels, going from that normal 100 volt per meter or 200 volt per meter test to a several thousand volts per meter test, sometimes those passing those test levels can be very, very difficult. We'll go over some of the common failures we see, some of the results that we see in there, and then determining the required test levels. This requires working hand in hand with the airframe manufacturer, with the airplane, deciding how much the field level is going to be attenuated from the exterior of the aircraft to the interior of the aircraft. So those are there's three topics basically we can look at, and I'm going to check into what the polling says. Okay, that's interesting. So a lot is understanding the compliance methods and determine the required test levels. All right, we'll launch into that, and we'll look at what we can learn from this. So military common sources of HIRF. The most common sources of HIRF are military and radar, civilian radar systems, both onboard, ground-based. It's also from other aircraft in the location. The high-powered radios, both the onboard and external radios. So if you have a radio that's running on board that's going to communicate over a long distance, that can actually cause more problems. We try to keep the antennas as far away from the any of this stuff as possible, but that's kind of what we try to do, is keep the antennas away. The other thing is TV broadcast antennas. Lots of times you're flying these, especially helicopters, they'll be flying right past the TV broadcast antennas, and that can produce some pretty high fields. The other point is satellite communication ground stations. These satellite communication ground stations, as you pass over them, they produce some very high fields. We talked a little bit about lightning strikes causing natural HIRF source. The good thing about a lightning strike is it's very short period. In other words, it's not going to be there for a long haul. So you have a disruption from a nearby lightning strike. You're going to have a short disruption, but it's not going to be there for a long period of time, whereas most of the HIRF things we talked about, the radar systems, both onboard and ground-based, those type of things are going to be there. Matter of fact, we take that radar system, we put it at the airport. So right where we're coming in for final approach, that's where we're going to put that radar system that can mess up your aircraft. But that's just the way it ends up being. But we try to maintain some distance away from them. For commercial aircraft, military aircraft, they're going to fly wherever they're going to go. So if we think about the risk and effects to this, the electromagnetic interference, this is the disruption of electronics. Usually this comes from a unshielded or poorly shielded pieces of equipment. This can be catastrophic if you're looking at a level A system. When you look at a level A system, level A systems are pieces of equipment that if they stop operating, you're no longer mission capable, or your flight is going to be disrupted in most cases. Worst case, obviously, is the plane falls out of the sky. We try to avoid that as much as possible. Other thing is critical system malfunctions. This can happen both for aircraft avionics or onboard medical devices. We've actually been seeing a lot more onboard medical devices going through RTCA DO-160 testing to be able to go on life flight type items. We see a lot of flight controls that are flight control systems because they're out there on the wing of the aircraft, and they're fully exposed to the HIRF environment. So they're fully exposed to the external environment. So like category G of RTCA DO-160 or some of the very high levels of 464. The other thing that we want to protect the HIRF from is data corruption. One of the worst cases is where the data is corrupted and it gives hazard misleading data to the pilot. So now the pilot is looking at data that's saying that altitude of the aircraft is this when it is not, or the other thing it can do is cause pilot fatigue. So now the pilot is looking at two different data sets. One is maybe an analog circuit, one is a digital circuit, and they're both saying that something is different. And what you end up having is now the pilot has to make that decision of which one is the more important, leading to pilot fatigue. So HIRF in aviation, we're going to be focusing mostly on this. HIRF is a larger concern in aviation due to the modern fly-by-wire aircraft that I talked about a little bit earlier. There are regulatory bodies for this. There's the FAA and EASA, or European Union Aviation Safety Agency. These all require HIRF protection and testing. Those are mostly focused on commercial. The test method and test levels are specified in a lot of the different standards. If we look at the military equipment, it's usually tested to like a mil standard 464 or ADS 37A. ADS 37A is more aimed at missiles, whereas mil standard 464 is aimed at systems on aircraft. And then commercial avionics are usually tested to RTCA DO-160 and SAE ARP 5583. 5583 is aimed at full vehicle and also components, whereas RTCA is really aimed at components and systems. Certification requirements. Some of the certification requirements. The equipment must demonstrate immunity to the HIRF environment. This can be very difficult. The HIRF environment is, like I said, changes per the mission of the aircraft and the location of the equipment on the aircraft. We'll kind of get into that a little bit as we go more into the certification. The testing can include lab simulation on the components or many times on the full system. So full system is recommended if it's a very complex system. So if you have something that's a very simple product or a very simple thing that's going on the aircraft, then it doesn't really need to do as a full system. But if there's a lot of interoperability between the systems, then that becomes where you have to do it as a full system. This is, kind of like a FADEC. If we're looking at a FADEC or something like electric power systems, flight controls, those type of things generally have to be tested as a system because they're going to interact with each other differently as you're going through the test. There's testing to determine the shielding effectiveness of the aircraft. SAE ARP 5583 has a lot of information on this. This is very important. Is an important step in the HIRF compliance because if you don't know what the aircraft's attenuation is, you could be under testing the components internal to the aircraft, especially if it's a plastic aircraft or like I like to joke about it, it's Wonder Woman's aircraft that has no shielding effectiveness. The compliance is to ensure that flight critical systems level A and level A displays remain operational during exposure to HIRF. There's some very good HIRF compliance steps per the FAA AC Advisor Circular 20-158 Alpha. We'll get more into that as we go along here. So let's talk about the HIRF compliance steps. When we're talking about HIRF compliance steps, the FAA Advisor Circular 20-158A is pretty much the best written out there. The first thing that we're going to have to do is we're going to go through and we're going to do a system safety assessment. This is the product that is going on this aircraft, is this product, if it stops working, what is the results? If it's a coffee maker, well, we don't really care. We can do without coffee for a time. But if it is something that is going to cause the aircraft to not operate, then we have to go through and do a little bit more system level HIRF protection. So this is where we make a decision on this. And just following the decision curve, do we know how the aircraft is being assessed? In other words, are we going to go through and we're in the military and we can test the whole aircraft at the high level test? Or are we going to do system level tests? So most commercial products, most commercial avionics equipment, they're going to do a system level test. Not doing the full aircraft, because doing the full aircraft, one, costs an incredible amount of money, but it also, you just don't have the access to the equipment to be able to do that. So you got to make a decision. Are you going to use generic transfer functions? In other words, you're going to go off of the generic transfer functions. Do you have aircraft that you've already designed that's got you have an airframe already that you know that the field levels on this aircraft internal are going to be, what is the attenuation going to be? Or you can take the new aircraft and you can do a low level swept or low level coupled test, where you inject a small field level outside of the aircraft. You measure the RF field that is accessed on the inside of the aircraft. That gives you your airframe's attenuation. Now you feed all of that information back to your system level of verification. So you now know that this component inside the aircraft has this much attenuation. Now you can do equipment test to be able to verify that the equipment is able to handle it. And then you do an integrated system level test. The system level test being that the full system is operating together, the level A system is operating together, and you're running the full field test at the same time. That's what we're kind of going to focus in on, is that full system level test. So here's a little bit about the advisory circular, the different standards. One of the things, and also a little plug to get involved in the SAE committee, AE4. The advisory circular, they're working on publishing the new later revisions to both of them, but we'll see as they go forward as to when those actually get published. So we're going to focus mostly on a level A system. The main reason why we're going to focus on a level A system is the compliance for a level B and a level C system. So these are the components that are less. Level B doesn't mean the airplane's going to fall out of the sky, but it's going to change its mission a little bit. Level C is that coffee pot we're basically talking about. The compliance tests for those two systems are very similar to what you have to do for a level A. Just the level A systems are a little bit more complicated. It's because the way the level A system has to be operated. So if we look at we're going to look at RF conducted and radiated susceptibility. If we look at RF conducted susceptibility, the test frequency range is from 10 kilohertz to 400 megahertz. And then the RF radiated susceptibility is from 100 megahertz to 18 gigahertz. And sometimes goes beyond. If you look at above those levels, sometimes we'll see that we'll do those test levels up to 40 gigahertz. I've seen all the way up to 50 gigahertz. If you look at mil standard 464, it does stuff all the way up to 50 gigahertz. There's a big overlap between a 100 megahertz and 400 megahertz between conductive susceptibility and RF susceptibility. One of the reasons why we have this large overlap there is because the field levels that are coupled onto this, for conductive susceptibility, it's really trying to repeat the radiated susceptibility at lower frequencies. But to couple a 10 kilohertz signal takes an incredible amount of energy. And in reality, most of the time, your coupling mechanism is going to be on cables, because anything that is below 200 megahertz is almost always on the cables, just due to wavelength and due to the size of the ports on most pieces of equipment. When you go from 200 megahertz to 400 megahertz, it's kind of a toss-up. You could be coupling through ports, but lots of times you'll be coupling through cables. And then 400 megahertz and above, it's usually slots and seams on the units. So that's why RFC, our radiated susceptibility, our RFRS, radiated susceptibility, has a large overlap there. Let's talk about the two different methods in RTCA DO-160. Mil Standard has very similar methods. They have a method for doing it in anechoic chamber. They also have a method for doing it in a reverberation chamber, 200 megahertz and above in a reverberation chamber. The anechoic method is in DO-160 is section 20.5, and then section 20.6 is for the reverberation chamber method. They use two different ways, two different paths to compliance, and two different paths to be able to run your test. So let's talk about the requirements for level A systems. A level A system requires all of the components to be functioning and working together. So when we talk about a level A system is like a FADEC. FADEC has several different components. It has fuel quantity measurements. It has igniters. It has all kinds of pressure sensors and things like that. All those things have to work together. All the interfaces have to be properly terminated. You're going to try and terminate everything as if it was on the aircraft. You want it to be set up as close to aircraft operation as you possibly can get. If you can't do that, you have to do something that makes it as close to simulation as possible. You're going to need to be able to monitor all the displays and the controls. So when you set these up, lots of times we'll end up using a shielded video cameras to monitor displays. We'll have several different components being monitored via in some cases we'll use different software to monitor the stuff, the equipment. Lots of times the system that we set up for this it's really got you gotta be a little creative in setting these up, especially when you have a lot of different components that have different failure criteria. So if you have a bunch of pressure sensors that have measurement, criteria for measuring the pressure, well, you have to be able to measure that as a system and all the system running together. So sometimes that proves to be a little bit difficult. Making a system to operate, so getting the full FADEC to operate and run so that you're able to do tests sometimes is much more difficult, in my opinion, than performing the test. That could be partly because we're experts on running tests. We're experts at doing HIRF testing. We are not experts on the customer's units. Matter of fact, if we become a customer, an expert on your unit, that means you've been in the lab a long time. We've been running a lot of tests. Sometimes that actually happens, but that meant we've been running those tests for a long period of time. And there are some test configuration and choices that are best to be avoided. I kind of referenced the two different specifications, an anechoic method and a reverberation chamber method. I kind of want to touch on this. If you look at a test unit that's being tested that has cables coming off of one side and some vents on the other side and maybe a display on one side and all these type of things, when you start looking at that, bombarding it from one aspect angle can be very difficult to obtain the full compliance test. And we'll talk a little bit more about that as we go. Let's talk about radiated susceptibility test parameters for level A systems. When we look at the test parameters, we're going to do a CW signal that's no modulation for the entire range from 10 kilohertz to 18 gigahertz. And like I said, sometimes all the way up to 50 gigahertz. We're going to do a square wave modulation. Square wave modulation is a 1 kilohertz square wave modulation. And then there's, when we're doing radiated susceptibility, there's pulse modulation. This starts at 400 megahertz. And 400 megahertz to 4 gigahertz, we're going to do a 0.4% duty cycle, or 4 microseconds, at a 1 kilohertz pulse repetition rate. And we're going to do a 1 microsecond, or 0.1% duty cycle, from 4 gig to 18 gigahertz. Now, these tests, I see these change periodically. Sometimes it's Department of Defense. Sometimes it's driven by different test levels that will do 10 microseconds. I've seen all the way up to 40 microseconds for this. There is a couple of test standards. Category R of RTCA DO-160 does 40 microseconds, but that's only at 150 volts per meter, so it's not extremely hard to do. Other modulations can be required. Sometimes we end up turning it on and off at a 1 hertz rate to represent the turning of the radar. Sometimes there's the other modulations are required. Every once in a while I see an FM modulation requirement. Matter of fact, I've seen that on several of the tests for 464. Sometimes I see it in ADS 37A. Default frequency steps for RTCA DO-160 is 100 steps per decade. More may be required, depends upon the standard. If you look at Mil Standard 464, they require much more steps. Mil Standard 461 requires a whole lot more steps. The I recommend if you have a failure in the frequency range to change that 100 frequencies per decade or 100 steps per decade. Change it to 200 steps per decade, get yourself a little bit more granularity so that you now have a better method and you know better where to design your filter for to be able to pass the test. So whenever there's a failure, we try to take more steps to be able to do this. The default dwell time at every frequency step is 3 seconds. But it can be longer or shorter dwell time can be used as dictated by the system characteristics. So what this really means is if you have a system and it takes 10 seconds to exercise the system, remember we talked about the level A system needs to be operating and function. So if we have a level A system and it takes 10 seconds for it to go through its full operation, well, that's our dwell time then. This comes into play a lot if you're looking at something like an actuator. An actuator, when an actuator runs and it starts to execute an actuation, lots of times that actuator will function in a 5-second window, but then have to wait a full minute. You can see how that would affect our test time. Our test time goes up exponentially because now we're spending more time just waiting. So you gotta specify your dwell time and try to make your system operate as quickly as possible to cut down on your dwell times. This is a little bit of confusion sometimes about the modulation, so I thought I'd throw in a screenshot about this. So what we call an unmodulated signal or CW signal is just that. It's a full signal. This is actually RMS levels. So when we see peak, we're not talking peak as in peak excursion. It's a peak excursion of the RMS modulated the wave. So when we see these things peak, that doesn't go to peak or peak voltage. It is an RMS measurement. And we'll talk a little bit more about that in this screen here. So on this screen, we're looking at the RF environments. You notice how it says peak and average. When we see that in the environments, when we see the peak and average, average means CW and square wave. It does not mean an average measurement. And there's no correlation between the peak of 1400 volts per meter, 700 to 1 gig, and 240 volts per meter CW and square wave. That average does not mean it's an average of the peak of the pulse modulation. So every once in a while we see somebody that says, "Oh, I wanted to do an average of that, figure to build a test at a lower level." There's really not a correlation there. Those are two different transmitters. One is a radar transmitting that with a 4 microsecond pulse width, and the other one is considered to be there all the time. Let's talk about conducted RF susceptibility. So now we're talking about the methods of compliance. So one of the things that we're going to do for conducted RF susceptibility, we're going to calibrate. We're going to do a calibration of the injection probe in a 50 ohm calibration plot. And when we do that, we're going to reach the current limit that's required per the standards. So there's several different current limits depending upon the level that you've found. This is where we have actually done some swept testing in the aircraft. We have found out what those field levels are going to be. And then what we do is we reproduce those field levels as we're doing this on a calibration. So we're going to make that current limit, reach that. And while we do it, we're going to measure the power it takes to reach those levels. During the induced current, during the test, when we're injecting the test level on the unit, when we're testing on the unit, we're going to reach those induced current levels. So our goal is to reach the induced current limit that is required. And if we do not reach that induced current limit, we're going to increase the forward power up to 6 dB. Now, this is directly out of RTCA DO-160, section 20. And when we do that, we need to be very clear that 6 dB, that is 4 times the power. So if during the calibration, it took us 100 watts to meet the current limit, and then we go and inject it on the EUT. And as we're injecting it on the EUT, it is a high impedance cable. We are going to drive to 400 watts on there. This can actually drive some pretty crazy test levels and pretty excessive amount of energy. So sometimes when we're doing this, we're going to have to either do a couple of things. We're going to cool the injection probes, and I'll show some pictures of how we go about that. Or we have to have cool down periods during the test. In other words, we'll be able to run for a short period of time, then we have to let everything cool down. Or the other thing that we do is we go in and grab some very large injection cores, if we can fit them on the cables. And later slides will show a little bit of why that sometimes is not possible. And then we will actually sit there and inject some of those levels. We've been seeing over the last few years, we see these test levels of 3 amp test levels. Where's that coming from? But periodically we'll see that we have to inject 3 amps on a test unit. And that can prove to be very difficult once you're injecting 3 amps of RF energy on a test unit. All right, here's an example of conducted RF calibration setup. So what we have here is we have an injection core. It's inserted in the calibration fixture. On the left side, we have a 50 ohm termination. On the right side, we have an attenuator that's feeding to our voltage, our system. It's usually a spectrum analyzer. And what we're going to do is we're going to develop the RF energy, and we're going to measure that RF energy across a 50 ohm source. And what that's going to tell us is what our current level is. When we're running this calibration, then we will actually do what we call a system check. I highly recommend doing a system check. System check's purpose is to verify that our injected power that's injected into our 50 ohm system and our monitor probe are all in sync. So what we're doing is we're injecting our calibrated limit that we just ran, and we're connected up to another 50 ohm termination, and we're measuring it with our current monitor probe. Remember how the standard, I just said in the standard, you're going to drive to that current limit. This makes sure that that monitor probe is functioning correctly, your injection probe is functioning correctly, and now when you go to apply it on the unit, now you're for sure getting the correct levels. So I highly recommend doing a system check. The last thing you want to do is after you've been running this for a week, go, oh yeah, our monitor probe wasn't correct. So this is one of those things that we try to do at most labs actually do this. So we talked about the systems and how complex the system can end up being. And this is an example of how complex those systems can be. So one of the things we find is in DO-160 and every one of the standards, they show a system as a box, 2 lines. A line going in one direction to a LISN, maybe a line going in another direction to an interconnecting cable or an IO cable. In most cases, we find that it is actually much more complicated than that. So as you can see, trying to get these current probes in place can prove to be difficult. So the standard calls out that we want to be 5 centimeters away from the EUT. So the EUT is that silver box on the right, and we're injecting on a cable, and then 5 centimeters between that is our injection core. Well, in this case, it's all sandwiched in there. You can see that it proves to be very difficult. It's not going to look exactly like the picture in the standard, and rarely does it, especially when you're looking at system as a full system test. Auxiliary cooling for 1 amp and more. So this is an example of one of the tests that we did. I think this was our Minneapolis lab that was doing this, our Bloomington, Minnesota. They were using liquid nitrogen. So we have a liquid nitrogen, a dewar of liquid nitrogen that's feeding into a system to cool the probe to be able to allow us to be able to do to be able to do much higher test levels, even though because most of the time these probes are designed for no more than 100 watts. So if we look at this probe and it's designed for 100 watts and we got to eject 400 watts, well, what we're going to end up doing is we're going to end up cooling that probe to be able to do this. And we have to be very careful not to cool the probe too much or too quickly, because now that probe becomes better conducting and the current can go higher. So what we've done is they put in a system to cool the probe and to regulate it. The other method of doing this is very large injection cores and things like that, which works just fine. The other thing we can do is run it for a short period of time, pause it, and let it cool off for a period of time. But this is for the very high levels test. Here is the test results from the Element Lab in Minneapolis. A couple of things to note in this. RTCA DO-160 allows us to do only 10 steps per decade. And I talked about 100 steps per decade. That's generally the rule. But below 100 kilohertz, so from 10 kilohertz to 100 kilohertz, 1 decade, they allow us to do 10 steps per decade. So that's what we did. We did 10 steps in that period. That's one thing to note. Another thing to note in this is where you see the RF energy did not reach the calibrated limit. So if you look at this, we're trying to inject that current. We're trying to reach that current on the EUT on the cable. As we're injecting that RF current on the cable, we're trying to reach the current limit. If we're not able to reach the current limit, it's going to go right past that calibrated limit. So here was our calibrated, we have a line that was our calibrated limit, the solid black line, and it goes up to that dotted line. That's 6 dB greater than the calibrated limit in the 50 ohm system. So wherever we see this current not reaching the level, where it dips down, the red line dips down below the top black line, we should see that the power has reached that plus 6 dB. So that's one thing to note when you're looking at data, is that if that is not the case, if let's say our red line was below that and our blue line was below that, we did not hit the correct test level. So just be aware of that and look for those type of things to make sure that you've got a good solid running system. All right, let's talk about failures. We're going to breeze through some of these things, but the power resets, this can happen due to poor internal grounding on the internal circuits, builds up RF energy, causes the powers to reset. Functional errors, these are usually caused by modulation affecting the digital circuits. When we have modulation, it's going to affect our digital circuits. When we have CW, it affects our analog circuits. For troubleshooting this on a component, what I will do is I will actually turn off the modulation, just run CW. Now it can guide me to the right circuit to be looking at. The other thing that we can see is hardware damage. This is usually due to high current getting into high voltage getting into the circuit, or current across some of the sensitive circuits. Audible noise, this is where we get a 1 kilohertz tone that runs on our systems. This is very similar to the noise that generates on your TV when the vacuum's running next to it, or like old TVs. The other thing that we see is, once again, the same thing as the modulation affecting the digital circuits, the CW affecting the digital circuits, degrading performance. All right, let's talk about radiated RF susceptibility. This is one of my favorites. I'm really going to focus mostly on the reverberation chamber. We can do this direct illumination, but like I said earlier, and we'll cover this a little bit better, but system A devices, it's very hard to get a very good test in this, so I'm going to focus mostly on a reverberation chamber. We're going to talk about mode stirring. Mode stirring is allowed. You can step. You can also do stepping, but you stop the tuner at discrete steps is allowed and keep the RF energy on. This is to make sure that you're actually developing enough dwell time for testing the unit. Reverberation chamber method requires, when you first put in your reverberation chamber, you need to do a field uniformity calibration. Now, well, I'm not going to cover a whole lot about this because this is something you can go out and buy a reverb chamber, and the people that design reverb chambers will do this test for you. Here at Element, we design our own reverb chambers and do this testing all of ourselves, but that's just because we've been doing it over the many of these over the years. Let's talk more about the calibration with the system in the unit. So to be able to do a calibration with the system installed in the chamber, first thing we do is we install the thing in the chamber. We inject a signal. We read that RF energy that's coupled on the receive antenna. Using the maximum receive power on the monitor antenna throughout that full rotation, we'll then run some calculations, and that tells us the field level that we're going to be generating inside the room. Here's an example of a reverberation chamber. There's basically a paddles, you have a chamber, you have no anechoic material on the walls, and you put your unit in there and you develop a bunch of field. We're going to just kind of breeze through that real quick. Here's an actual reverberation chamber. This is a reverberation chamber in our Minneapolis lab. This reverberation chamber, we have a very simple EUT there. We've got the paddle up here. We've got a transmit antenna. We have a receive antenna. And what we're going to do is inject a signal, and we're going to receive that signal, and we're going to verify all the field levels. But that's a very simple EUT. Pretty simple. It's got a couple of cable coming off of it, and it's got a couple of other cables. That's about it. This is typically what we see. This is our normal reverberation chamber test. So we've got an EUT, these big copper boxes. We've got several different EUTs in here. When we look at all these EUTs in there and all of this, this is where that reverberation chamber comes into play. If I was to try to do this direct illumination, I'd have to be able to hit test units up in the middle of the bench, test units on the side of the bench. And when I try to generate those fields on those, laying this out can be a nightmare. And trying to achieve those levels, especially internal to the in the center of the table, you're going to be either over testing the product on the edge of the table, or you're going to be under testing the product inside the table. And this is where the reverberation chamber is the preferred method to be able to do this testing, especially on systems like this. Here's an example of the calibration. So we did a loaded calibration inside that chamber. And as we did a loaded calibration, we injected 1 watt. We went through our calculation on our receive antenna. And with 1 watt, we were able to achieve roughly 80 dB. So if we look at our first frequency at 1 gigahertz, with 1 watt, we were able to achieve just slightly under 80 dB. So if we were to do this test and run it all the way up to 800, we'd have to put 20 more dB of power into this chamber. Here's a final run on this test. We did a product. We're doing 5,000 volts per meter. It took about 60 dBm to generate the field. So this gives us our clear test that we did 1 to 2 gigahertz with that reverberation chamber. So let's talk about some failures. So failures that we see inside the chamber, this is once again is usually due to poor grounds. In some cases, due to overvoltage seen on the control circuits. So what we'll see is we'll overdrive the RF energy will couple to a cable, the RF energy will couple through a port and generate much higher fields. And what will happen internal to the unit, it locks up the control circuits. Same thing as the last one, but usually a little bit more difficult is the modulation affecting our digital circuits. Remember, we're doing this low duty cycle modulation that has extremely high fields, so that sometimes can cause some issues. And we're also going to be doing CW and square wave measurements. Our hardware damage, this is something I'll cover in another slide here going forward, but basically what we've seen is RF energy coupling to the components with so much energy coupling to it that it appears like an ESD event. Audible noise, just like the last one, we end up with the 1 kilohertz audible noise coupling to the different receivers and transmitters and affecting performance. Our performance gets affected by those digital circuits and the CW affecting our analog circuits. Let's talk a little bit more about the some events. Let's take an example I saw a few years ago. I've actually seen this more than once over the last few years. When I briefly described the EUT, it was basically an internal circuit card. The EUT has a backplane that has, when you take the circuit card and it's connected into the backplane, what we end up finding is that the backplane and the circuit card work together as if really as a 1/2 wave monopole antenna. If you look at a half wavelength of 4 gigahertz, we're looking at only 1.48 inches, or 3.7 centimeters. The EUT had a horizontal slot running next to it. So if we look at this circuit, the circuit is basically a half wave antenna running right next to a ventilation slot that had a horizontal slot running next to it. So its coupling mechanism is basically 0 dB. But when we go through and we look at a mono wave antenna, which is the way this was functioning, it's got 2 to 4 dB. Our RF field level on the outside of the EUT was 7,200 volts per meter, category L of RTCA. This coupled approximately, if we look at the gain of that of the monopole antenna, it's going to couple about 9,000 volts per meter to 14,000 volts per meter. When we look at that, it caused ESD damage. When we went through and did failure analysis, it looked just like a ESD had damaged. All right, that kind of brings us to some polling questions. So at what stage is your HIRF compliance program presently at? Are you at the point where you're defining the specifications? Are you designing to the specifications, presently testing, clarifying results, and failure analysis, just like I was talking about on that ESD page? So let's just go through this for a little bit. As when you were talking about defining specifications, this is usually where you're at the very beginning. Now you're at, hopefully you did this long before you started the design. And then run straight through to designing for the specifications. The designing of the specifications, this is where hopefully you're building it for that, presently in the middle of the test. And then clarifying the results. Clarifying the results can be very difficult. And then the failure analysis. I'll leave that open for just a little bit, but we're running short on time, so I'm going to jump straight to the next slide here. All right, so we've got defining specifications is the winner on that. So here's a couple of things, lessons learned on what not to do. One of the things is, if we look at this system over here, very uncomplicated system, we could probably do that in an anechoic chamber. But if that was a complex system, we would not want to do it in an anechoic chamber. And I think the other thing is that we would like to see is on the right side, we need to have some good setup to be able to keep that RF energy inside the chamber so it doesn't ride out on the unit. Ride out into the anechoic and out and go and damage some support equipment. We can do things to reduce loading. In this case, what we did is we basically built a tent over top of it with a just aluminum foil. And what we're doing is we're testing other components at a higher level, and the components that are under that or under the tent are at a lower level. So we're going to be able to do stuff that can reduce the loading in the chamber and allow us to be able to test to higher levels. HIRF protection measures, we kind of talked about this, is shielding, use of conductive enclosures and well-shielded cables. Designing your filters to suppress the incoming injections, especially from 10 kilohertz to 100 megahertz. The grounding and bonding. This prevents a buildup of EMI on the surface, and it gives you a low impedance path, low inductance path to the airframe. Sometimes redundancy is another way of doing it. Is you can have two products. One is a dissimilar design. That gives you your system a little bit more stability. And that brings us to our last polling question. So would you like to follow up with the help troubleshoot and discuss this topic with us further? yes, no, and please follow up with an email, and I'll open up that polling. And we would be happy to help you troubleshoot or to help you with figuring out what's your test levels and be able to do these type of tests. We do these tests all the time. I like to be able to help you with your products. And like I said, we do a lot of this. Real quick on final commentary and summary. Level A systems are not easy. They require a high power amplifiers, high power antennas, probes, and most importantly, very complex test setups. A lot of the issues that we see during the test can be solved by having a very clearly written test procedure, well written and well thought out, especially what is considered a failure, what is not considered a failure. Test setups for level A systems, like we talked about on one of the screens back there, is that they rarely look like the pictures in DO-160. We make the pictures in DO-160 very clear, so that's easy for usual setups, but not for things like that. Thank you. And that opens up for question and answers. If anybody has any questions.
All right, everybody, this is Mike yet again. We've got an open floor for Q&A to Mike and Scott. Feel free to type any questions you have into the Q&A response box or into attendee chat, and our team will speak up and fire them off of Mark and Scott. Got a good 4 minutes remaining left, so any questions at all? Well, real quick, we just got one in. We have somebody that says they make a component for various systems. Do I need to perform HIRF testing on the component, or will the end user perform this testing on the system? So, really good question there between components and system level differences, Scott.
Yeah, so typically we try to do the component. When we looked at one of the slides, it said doing the components and then integrating it into the system. Because of the complexity of a system level test, the last thing you want is your component, the one component you designed, to cause the is for your component to cause the system level test to take much longer and to be doing some troubleshooting. So I highly recommend testing the component and do the component and do the component and do the system level.
Outstanding. Ooh, another really good one. Scott, what was a memorable or challenging HIRF project that you've worked on?
I've actually worked on a lot of these over the years. I think one of the greatest ones that I thought was very challenging was a brake stack, because the brake stacks have very high level test. And when you go to do a brake stack, test, the brake stacks basically are carbon, which is what we use to line our anechoic chambers to drive up a lot of to suck up energy. So what ended up happening is we ended up having a lot of energy driven into the brake stack. So we had to actually come up with a way of blocking away the carbon on the brake stack, yet testing the brake stack itself.
Outstanding. We actually have a question for me in here, which is really, really nice. Just so everybody is aware, our audience, the presentation slide deck and actually a copy of this presentation will be posted to the element.com YouTube channel. If you want to subscribe and follow that channel, you'll definitely see that as soon as we post it up after this is complete. And Scott, we got another question for you. And it was labeled as a wayside question, but in ADS-37 alpha, they think it calls for RMS levels rather than peak for table 1 part A. That always struck me as odd, and I quote, since 461 calls for peak in RS-130. Is that really the intention?
Yeah, so when they're talking about peak there, they're actually talking about not actually as in peak amplitude. It's not an RMS versus peak. It is peak as in a low duty cycle pulse. So they're calling it out as a peak excursion of the RMS signal. So it's not actually an RMS versus peak. It is just a peak. They're always talking RMS on this.
And then we've got time for one last one. And we have the test setup layout you showed in the reverb chamber, Scott. Is that representative of the EUT location on the platform? Are the test support equipment sim boxes also exposed to the fields in the reverb chamber?
So in the one that we were showing, that is those components, the only components that were on that bench that are not actually part of the EUT. The only components that were on that were then the LISNs, the line impedance stabilization networks. There was boxes in there that have components that would see a lower level. So what we've done is they're inside a solid metallic box. Lots of times we don't put in some of the components because they're not actually they're going to be installed internal to the air engine, so such as some sensors that go into the engine itself, like the ends of the igniters. The ends of the igniters are in a metal portion of the engine, so they're not actually tested. So in that case, most of those boxes were actually were going to be installed and are under test.
Well, cool stuff, Scott. Well, I know the questions are still coming in, but we've got Mark's and Scott's contact information there directly, so feel free to reach out to them directly with any questions regarding EMI, EMC, HIRF testing, as well as our services in product qualification testing across the board. We're more than happy to keep those answers coming, as well as to help out with any projects that any of you, our audience, has on the block. And of course, you can reach out to Element experts through contact.us@element.com. We're happy to respond there as well. Just a quick reminder, we are going to post this webinar in its entirety on our YouTube channel, so feel free to follow and subscribe. I encourage you to see content like this as it's published, as well as additional technical content from all of our subject matter experts across Element. Thank you so much, Mark and Scott, for joining us and providing a little bit of insight into your day as well as your expertise. This has been an absolute blast, and I'm sure our audience shares that sentiment as well. But thank you, everybody, for joining us, and feel free to reach out and, of course, to review this material at your leisure using our YouTube channel. Thank you so much.
Thank you.